Find the limit as x goes to 0 of 2 minus the 10th root of 1024 plus x divided by x, not using L'Hopital's rule. So we obviously can't just let x tend to 0, as then we would be divided by 0, which isn't allowed. So we have to evaluate this limit using a different method. Let's begin by setting y to the 10th power to be equal to 1024 plus x. This means that y is equal to the 10th root of 1024 plus x, and x is equal to y to the 10th power minus 1024. Now, we've made a change of variable, so we need to incorporate this information into the limit. So as x goes to 0, y goes to the 10th root of 1024, which is just equal to 2. It's really important that you incorporate this information into the limit, as if you didn't, we wouldn't get the same answer. This implies that we can rewrite our limit as the limit as y approaches 2 of 2 minus y divided by y to the 10th power minus 1024. Now we can rewrite the numerator as minus 1 multiplied by y minus 2, and we can rewrite the denominator as y to the 10th power minus 2 to the 10th power, and we can actually go a step further and rewrite this as y to the 5th power minus 2 to the 5th power multiplied by y plus 2 to the 5th power. Excuse me, that should actually be y to the 5th power plus 2 to the 5th power. And the reason for doing so will become clear as we go through the problem. Now, paying attention to the factor on the left hand side, that is y to the 5th power minus 2 to the 5th power, we can use the formula highlighted in yellow to rewrite that as y minus 2 multiplied by y to the 4th power plus 2 times y cubed plus 2 squared times y squared plus 2 cubed times y plus 2 to the 4th power. This allows us to rewrite our limit as the limit as y approaches 2 of minus 1 multiplied by y minus 2 divided by y minus 2 multiplied by y to the 4th power plus 2 times y cubed plus 2 squared times y squared plus 2 cubed times y plus 2 to the 4th power, all multiplied by y to the 5th power plus 2 to the 5th power. And of course we can cancel a factor of y minus 2, so we're just left with the following limit. And now we can just let the limit tend to 2 without worrying about dividing by 0, which gives us a final answer of minus 1 divided by 5120. Solve the limit as x goes to 0 of a minus the nth root of a raised to n plus x divided by x, where a and n are natural numbers. Now we can't just let x go to 0, because then we would be divided by 0. So we're going to solve this limit via two different methods. The first is a change of variable, and second is L'Hopital's rule. So for method 1, let's begin by setting y raised to n to be equal to a raised to n plus x. This implies that x is equal to y raised to n minus a raised to n. Also, we need to incorporate this change of variable into the limit. So we have as x goes to 0, y goes to a. We get this from solving y raised to n is equal to a raised to n plus x by letting x be equal to 0, then taking the nth root of both sides of that equation. This allows us to rewrite our limit as the limit as y approaches a of a minus y divided by y raised to n minus a raised to n. Now we can factor a minus 1 out of the numerator, and we have the limit as y goes to a of minus 1 multiplied by y minus a divided by y raised to n minus a raised to n. And we can use the following formula to rewrite the denominator as the following. Now substituting this expression into our limit for our denominator, we're left with the following limit, where we have a y minus a in the numerator and a y minus a in the denominator, which we can go ahead and cancel. And we're left with the limit as y goes to a of minus 1 divided by y raised to n minus 1 plus y raised to n minus 2 multiplied by a plus so on and so forth plus y multiplied by a raised to n minus 2 plus a raised to n minus 1. And if we just let y tend to a, we're left with the following. Now, a raised to n minus 2 multiplied by a raised to 1 can be rewritten as a raised to n minus 2 plus 1, which is equal to a raised to n minus 1. We have n of these, so we're left with a final answer of minus 1 divided by n multiplied by a raised to n minus 1, which is the final answer for method 1. Now on to method 2. If we let x tend to 0 in the numerator and the denominator, we have a limit of indeterminate form 0 over 0, and we can use L'Hopital's rule, which was stated for our specific problem, to solve this limit. Now to take the derivative of the numerator, we have to use the chain rule and the power rule, so we have 0 minus 1 divided by n multiplied by a raised to n plus x, all raised to 1 divided by n minus 1 multiplied by 1 divided by the derivative of the denominator, which is just 1. Simplifying, we have the limit as x goes to 0 of minus 1 divided by n multiplied by a raised to n plus x, all raised to 1 minus n divided by n, where all we've done to simplify the exponent is cross multiply. Now if we just let x tend to 0, we're left with minus 1 divided by n of a raised to n all raised to 1 minus n divided by n. A raised to n all raised to 1 minus n divided by n can be simplified by just multiplying the n by 1 minus n divided by n. So we have a raised to n multiplied by 1 minus n divided by n, and the n's cancel, so we're left with a raised to 1 minus n. And if we rewrite a raised to 1 minus n is 1 over a raised to n minus 1, we get the following final answer of minus 1 divided by n multiplied by a raised to n minus 1, which agrees with our answer from method 1. Find the limit as x approaches 0 of the fourth root of 16 plus x minus 2 divided by x. Let's begin by setting y to the fourth power to be equal to 16 plus x. Then we can rewrite y as the fourth root of 16 plus x. And we also have that x is equal to y to the fourth power minus 16. Also, as x goes to 0, y goes to 2. Now we can rewrite our limit as the limit as y approaches 2 of y minus 2 divided by y to the fourth power minus 16. Now if we rewrite the numerator as y to the fourth power minus 2 to the fourth power, it's pretty easy to see that we can factor it as y squared minus 2 squared multiplied by y squared plus 2 squared. And then we can actually rewrite this part here as y minus 2 multiplied by y plus 2. So we can rewrite the limit as y approaches 2 of y minus 2 divided by y minus 2 multiplied by y plus 2 multiplied by y squared plus 2 squared. We have a factor of y minus 2 in the numerator and a factor of y minus 2 in the denominator. We can cancel those, and we have the limit as y approaches 2 of 1 divided by y plus 2 multiplied by y squared plus 2 squared. Now if we just let y tend to 2, we have the limit as y approaches 2 of 1 divided by y plus 2 multiplied by y squared plus 2 squared is equal to 1 over 32. Therefore, the limit as x approaches 0 of the fourth root of 16 plus x minus 2 divided by x is equal to 1 over 32, which is the final answer to this problem. To find the limit as x approaches 0 of the cube root of 2197 plus x minus 13 divided by x. Let's begin by setting y cubed to be equal to 2197 plus x. This implies that y is equal to the cube root of 2197 plus x, and also x is equal to y cubed minus 2197. Also note that as x goes to 0, y goes to 13. This means we can rewrite our limit as y approaches 13 of y minus 13 divided by y cubed minus 2197. Now y cubed minus 2197 is equal to y cubed minus 13 cubed, which we can simplify using the difference of cubes formula. We have y cubed minus 13 cubed is equal to y minus 13 multiplied by y squared plus 13y plus 169. This means we can rewrite our limit as y approaches 13 of y minus 13 divided by y minus 13 multiplied by y squared plus 13y plus 169. Notice that we have a y minus 13 in the numerator and a y minus 13 in the denominator. We can cancel those, and we're left with the limit as y approaches 13 of 1 divided by y squared plus 13y plus 169. Now if we just let y tend to 13, we have 1 divided by 169 plus 169 plus 169, which is equal to 1 divided by 507. Therefore, we have that the limit as x approaches 0 of the cube root of 2197 plus x minus 13 all divided by x is equal to 1 divided by 507, which is the final answer to this problem. To find the limit as x approaches 0 of the cube root of 19,683 plus x minus 27 divided by x. Now, we can't just let x tend to 0 as we would be dividing by 0, so we have to rearrange our limit into a more suitable form. Let's begin by setting y cubed to be equal to 19,683 plus x. This implies that y is equal to the cube root of 19,683 plus x, and x is equal to y cubed minus 19,683. Also, as x goes to 0, y goes to 27. Because we've made a change of variable, we need to incorporate that new information into the limit. So our limit becomes the limit as y approaches 27 of y minus 27 divided by y cubed minus 19,683. Now we can rewrite the denominator as y cubed minus 27 cubed because because the cube root of 19,683 is equal to 27. Now using the difference of cubes formula, we can rewrite y cubed minus 27 cubed as y minus 27 multiplied by y squared plus 27y plus 27 squared. This allows us to rewrite our limit as the limit as y approaches 27 of y minus 27 divided by y minus 27 multiplied by y squared plus 27y plus 27 squared. And of course we have a factor of y minus 27 in the numerator and a factor of y minus 27 in the denominator. We can cancel those and our limit becomes the limit as y approaches 27 of 1 divided by y squared plus 27y plus 27 squared. And now we can just let y tend to 27 without dividing by 0. So we have 1 divided by 27 squared plus 27 squared plus 27 squared, which is just equal to 1 over 2,187. Therefore, we have that the limit as x approaches 0 of the cube root of 19,683 plus x minus 27 divided by x is equal to 1 over 2,187, which is the final answer to our problem. Find the limit as x approaches 0 of 2 minus the square root of x plus 4 divided by x. Now, we can't just let x tend to 0 because then we would be dividing by 0, which isn't allowed. So we have to rearrange this limit so that we can evaluate it. Let's begin by setting y squared to be equal to x plus 4. This implies that y is equal to the square root of x plus 4 and x is equal to y squared minus 4. Also note that as x goes to 0, y goes to 2. We need to incorporate this fact into what we're about to rewrite the limit as, because we've made the change of variable. So this means that we can rewrite our limit as the limit as y approaches 2 of 2 minus y divided by y squared minus 4. Now we can rewrite y squared minus 4 as y squared minus 2 squared. And we can use the difference of squares formula, which I've written right here, to rewrite our denominator as y minus 2 multiplied by y plus 2. So our limit becomes the limit as y approaches 2 of 2 minus y divided by y minus 2 multiplied by y plus 2. We can actually factor a minus 1 out of the numerator, so we have the limit as y approaches 2 of minus 1 multiplied by y minus 2 divided by y minus 2 multiplied by y plus 2. Now we can go ahead and cancel the factor of y minus 2 in the numerator with the factor of y minus 2 in the denominator, and doing so we have the limit as y approaches 2 of minus 1 divided by y plus 2, and we can just let y tend to 2 without worrying about dividing by 0, which gives us an answer of minus 1 over 4. Now there's actually another way to solve this problem, and we can do that by rationalizing the numerator. We can do that by multiplying the numerator and the denominator by 2 plus the square root of x plus 4. Multiplying out the numerator, we have 4 plus 2 times the square root of x plus 4 minus 2 times the square root of x plus 4 minus x minus 4, which is just equal to minus x, which we can factor out a negative 1 from, and we have negative 1 multiplied by x. So we can rewrite our limit as the limit as x approaches 0 of minus 1 multiplied by x divided by x multiplied by 2 plus the square root of x plus 4. And we can actually cancel a factor of x, and we're left with the limit as x approaches 0 of minus 1 divided by 2 plus the square root of x plus 4, which is also equal to minus 1 over 4. Therefore, the limit as x approaches 0 of 2 minus the square root of x plus 4 divided by x is equal to minus 1 over 4, which is the final answer to our problem. Find that the limit as x approaches 0 of 3 minus the cube root of x plus 27 divided by x. Now we can't just let x go to 0, because then we would be dividing by 0, which isn't allowed. So we have to evaluate this limit using different methods. So let's begin by setting y cubed to be equal to x plus 27. This implies that y is equal to the cube root of x plus 27 and that x is equal to y cubed minus 27. Also, as x goes to 0, y goes to 3. We need to incorporate this fact into what we're about to rewrite the limit as. So our limit becomes the limit as y approaches 3 of 3 minus y divided by y cubed minus 27. Now we can rewrite the numerator as minus 1 multiplied by y minus 3, and we can rewrite the denominator as y cubed minus 3 cubed, because 3 cubed is equal to 27. Now using the difference of cubes formula, which we've written in yellow right here, we can factor the denominator as y minus 3 multiplied by y squared plus 3y plus 3 squared. This allows us to rewrite our limit as the limit as y approaches 3 of minus 1 multiplied by y minus 3 divided by y minus 3 multiplied by y squared plus 3y plus 3 squared. Now we have a factor of y minus 3 in the numerator and a factor of y minus 3 in the denominator. We can cancel those, and we're just left with the limit as y approaches 3 of minus 1 divided by y squared plus 3y plus 3 squared. Now we can let y tend to 3 without worrying about dividing by 0, which was our issue before, and that gives us minus 1 divided by 27. Therefore, the limit as x approaches 0 of 3 minus the cube root of x plus 27 divided by x is equal to minus 1 over 27, which is the final answer to our problem. We solve the following limit using two different methods. The first will be the standard change of variable method that we've used in other videos, and the second will be L'Hopital's rule. Now, we can't just let x tend to 0 because then we would be divided by 0, which isn't allowed. So for the first method, let's make the following change of variable. And of course, y is equal to the following, and we can also solve for x in the same way. And because we've made a change of variable, we need to incorporate this information into the limit. So as x goes to 0, y goes to 5. This allows us to rewrite our limit in the following form. Now we can factor a minus 1 out of the numerator, and we can rewrite the denominator as y to the 10th power minus 5 to the 10th power. Now we can actually go a step further and factor the denominator in the following way, so that we have the limit as y goes to 5 of minus 1 multiplied by y minus 5 divided by y to the 5th power minus 5 to the 5th power multiplied by y to the 5th power plus 5 to the 5th power. And now using the following identity, we can rewrite the first term in our denominator as y minus 5 multiplied by y to the 4th power plus 5 y cubed plus 5 squared y squared plus 5 cubed y plus 5 to the 4th power. And substituting that into our limit, we have the following. So we have a factor of y minus 5 in the numerator and a factor of y minus 5 in the denominator, and we can cancel those so that we're left with the following limit. And we can just let y tend to 5 now without worrying about dividing by 0, which gives us the following answer. So that's it for method 1. Now on to method 2. From before, we know that the denominator tends to 0. This is actually the case for the numerator, so we can go ahead and apply L'Hopital's rule because we have an indeterminate form of 0 over 0. L'Hopital's rule basically says what we've put on the screen here. This is the case when you have an indeterminate form of 0 over 0 or plus or minus infinity over plus or minus infinity. So differentiating the denominator, we just have 1. And we can use the power rule and the chain rule to differentiate the numerator in the following way, which we can rewrite in the following form because we have a negative exponent, so we can make it positive by bringing it down into the denominator. Now we can let x tend to 0 without worrying about dividing by 0, and we get the same answer as we did in method 1, so both of the answers agree. Find the limit as x approaches 0 of 9 minus the cube root of 729 plus x divided by x. Now we can't just let x tend to 0 because then we would be dividing by 0, which isn't allowed. So we have to use a different method in order to evaluate this limit rather than evaluate it directly. Begin by setting y cubed to be equal to 729 plus x. This implies that y is equal to the cube root of 729 plus x, and that x is equal to y cubed minus 729. Also, as x goes to 0, y goes to 9. Since we've made a change of variable, we need to incorporate this change of variable information into the limit. Therefore, we can rewrite our limit as the limit as y approaches 9 of 9 minus y divided by y cubed minus 729. Now we can rewrite the numerator as minus 1 multiplied by y cubed minus 9, and we can rewrite the denominator as y cubed minus 9 cubed. Rewriting the denominator in this form allows us to use the difference, well, it makes it clear that we can use the difference of cubes formula to rewrite it as y minus 9 multiplied by y squared plus 9y plus 9 squared. Now we can rewrite our limit as the limit as y approaches 9 of minus 1 multiplied by y minus 9 divided by y minus 9 multiplied by y squared plus 9y plus 9 squared. Now we have a factor of y minus 9 in the numerator and a factor of y minus 9 in the denominator. We can cancel those, and the limit becomes the limit as y approaches 9 of minus 1 divided by y squared plus 9y plus 9 squared. We can just let y tend to 9 without dividing by 0. In doing so, we get an answer of minus 1 divided by 243. Find the limit as x approaches 1 of the square root of 2 minus x divided by x minus 1. Now, when you're evaluating limits that involve square roots, what you want to do is try to rationalize the numerator or denominator depending upon where the square root is located. We can do that by multiplying the numerator and the denominator by the square root of 2 minus x plus x for this particular problem. Multiplying out the numerator, we see that we have the square root of 2 minus x multiplied by the square root of 2 minus x plus x, which is equal to 2 minus x plus x times the square root of 2 minus x multiplied by the square root of 2 minus x squared. The square roots cancel, and we're just left with 2 minus x squared. And in this particular problem, what we're going to do is just leave the denominator as it is. So our limit becomes the limit as x approaches 1 of 2 minus x squared divided by x minus 1 times the square root of 2 minus x plus x. Now, You might be unsure how to progress at this point. What you want to do is factor out a minus 1 from the numerator. So you have minus 1 multiplied by x squared plus x minus 2. And what we can do is rewrite this expression as minus 1 multiplied by x plus 2 multiplied by x minus 1. So our limit becomes a limit as x approaches 1 of minus 1 multiplied by x plus 2 multiplied by x minus 1 divided by x minus 1 multiplied by the square root of 2 minus x plus x. Notice we have a factor of x minus 1 in the numerator and the denominator. We can go ahead and cancel those, and we have the limit as x approaches 1 of minus 1 multiplied by x plus 2 divided by the square root of 2 minus x plus x. Now what we can go ahead and do is let x tend to 1. So we have minus 1 multiplied by 1 plus 2 divided by the square root of 2 minus 1 plus 1, which is equal to minus 3 over 2. Therefore, we have the limit as x approaches 1 of the square root of 2 minus x divided by x minus 1 is equal to minus 3 divided by 2, which is the final answer to this problem. Find the limit as x goes to 0 of the square root of 2 minus e raised to x minus e raised to x, all divided by e raised to x minus 1. Now we can't just let x go to 0, as we would then be divided by 0, which isn't allowed. So we're going to solve this limit via two different methods. The first method that we're going to use is going to be a change of variables. So we'll begin by setting y squared to be equal to 2 minus e raised to x. This implies that y is equal to the square root of 2 minus e to the x, and e raised to x is equal to 2 minus y squared. And as x goes to 0, y goes to 2 minus e raised to 0, which is equal to 1. Because we're doing a change of variables, we have to incorporate this information into the new limit which we're about to write. So our limit becomes the limit as y approaches 1 of y squared plus y minus 2 divided by minus y squared minus 1 plus 2. Now we can actually factor a minus 1 out of the denominator and simplify it. So we have the limit as y approaches 1 of y squared plus y minus 2 divided by minus 1 multiplied by y squared minus 1. And notice that we can actually rewrite the numerator as y plus 2 multiplied by y minus 1. And we can rewrite the denominator now as minus 1 multiplied by y minus 1 multiplied by y plus 1. So we can now let y tend to 1 without worrying about dividing by 0. Doing so, we get a final answer of minus 3 divided by 2. So that's the answer for method 1. For method 2, we're going to rationalise the numerator of our limit. We can do this by multiplying the numerator and the denominator by the square root of 2 minus e raised to x plus e raised to x. Multiplying out the numerator, the square roots cancel, and we're left with the limit as x approaches 0 of 2 minus e raised to x minus e raised to 2x, all divided by e raised to x minus 1, multiplied by the square root of 2 minus e raised to x plus e raised to x. Now, if we factor a minus 1 out of the numerator, we can rewrite the numerator as minus 1 multiplied by e raised to 2x plus e raised to x minus 2. Paying attention to the numerator, we have e raised to 2x, which is basically e raised to x multiplied by e raised to x, and we have an e raised to x here. So we can factor the numerator as follows. We have minus 1 multiplied by e raised to x plus 2 multiplied by e raised to x minus 1. Now the reason for doing so becomes clear. We are now able to cancel the e raised to x minus 1 in the denominator with the e raised to x minus 1 in the numerator, and we're left with the limit as x goes to 0 of minus 1 multiplied by e raised to x plus 2 divided by the square root of 2 minus e raised to x plus e raised to x. And now we're able to actually let x tend to 0 without dividing by 0, and we get the same answer as before, minus 3 divided by 2. So we can't just go ahead and plug in x is equal to 2, because then we would have 0 in the denominator and we're not allowed to divide by 0. So let's just begin by factoring out an x squared from the denominator. So we have the limit as x approaches 2 of the square root of x plus 2 minus x divided by x squared multiplied by x minus 2. Now we're going to go ahead and rationalise the numerator. So we're going to multiply by its conjugate, which is just the square root of x plus 2 plus x divided by the square root of x plus 2 plus x. This is equal to the limit as x approaches 2. The square root of x plus 2 multiplied by the square root of x plus 2 is just x plus 2. And we're going to have x multiplied by the square root of x plus 2 minus x times the square root of x plus 2 minus x squared. And we're not going to multiply out the denominator, so we're just going to have x squared multiplied by x minus 2, all multiplied by the square root of x plus 2 plus x. Now these two cancel each other out, and we're just left with the limit as x approaches 2 of x plus 2 minus x squared divided by x squared multiplied by x minus 2 multiplied by the square root of x plus 2 plus x. Now what I'm going to do is factor in minus 1 out of the numerator. So we're going to have minus 1 times the limit as x approaches 2 of x squared minus x minus 2 divided by x squared times x minus 2 times the square root of x plus 2 plus x. Now notice that we can factor the numerator as x minus 2 times x plus 1. So we can rewrite our limit as minus 1 multiplied by the limit as x approaches 2. Now this x minus 2 will cancel with this one, so we're just left with x plus 1 divided by x squared multiplied by the square root of x plus 2 plus x. At this point we can just go ahead and plug in x is equal to 2, so we're going to have minus 3 divided by 16, and that is the final answer to this problem. If we were to just let x go to 0, in the numerator we would of course have 0, and in the denominator we would have 0 plus sine of 0, which is also just equal to 0. So we have a limit of the form 0 over 0, and in order to evaluate the limit, what we're going to do is use something called L'Hopital's rule. L'Hopital's rule basically says that if you have a limit as x approaches c of a function f of x divided by another function g of x, this limit is equal to the limit as x approaches c of the derivative of f of x divided by the derivative of g of x, given that f and g are both differentiable at c and that the limit is of indeterminate form 0 over 0 or plus or minus infinity over plus or minus infinity. Now, our limit here is of indeterminate form 0 over 0, and the numerator and the denominator are both differentiable at 0, so we can go ahead and apply L'Hopital's rule to this problem to try and solve it. So doing that, we have the limit as x approaches 0. Now, we can rewrite the square root of x as x raised to 1 over 2, and in order to take the derivative of x raised to 1 over 2, we just need to use the power rule. So we bring the power down to the front, and then we subtract 1 from the power. So we have 1/2 multiplied by x raised to minus 1/2, and we can also rewrite this as 1 divided by 2 multiplied by the square root of x. So all we've done is bring this negative power down to the denominator and rewrite it in this form here. So in the numerator we just have 1 divided by 2 times the square root of x, and in the denominator we also just have 1 divided by 2 times the square root of x. In order to take the derivative of sine of the square root of x, we need to use the chain rule. So we take the derivative of the outside part, and then we take the derivative of the inside part, and we multiply those two results together. So we have cosine of the square root of x multiplied by 1 over 2 times the square root of x. Now, in order to simplify our function, what we're going to go ahead and do is multiply the numerator by 2 times the square root of x and the denominator by 2 times the square root of x. Doing so, we have the limit as x approaches 0. So 1 over 2 times the square root of x times 2 times the square root of x is just 1, as these two cancel. We have the exact same here, and these two cancel, and we're just left with cosine of the square root of x. Now, if we just let x tend to 0, we have 1 over 1 plus cosine of 0, which is just equal to 1 over 1 plus 1, and that gives us the final answer of 1 over 2.